Hey everyone, and welcome back to The Explainer. Today, we're going to demystify the hidden world of control systems that basically govern our everyday lives. It's so easy to just look around our homes or workplaces and expect things to magically work, but right behind the scenes, there is this totally fascinating architecture of engineering making it all happen. In this Explainer, we're focusing entirely on one specific, incredibly common setup, the open-loop system. We're going to look at what it is, how it somehow manages to operate without any feedback at all, and why it's both brilliantly simple and, well, incredibly flawed.
Okay, let's dive right in. Here's our roadmap for today. First, we'll look at the anatomy of control systems. Second, defining the open loop. Third, we'll hit some real-life appliance examples. Fourth, the open loop advantages. And finally, the fatal flaw.
Section 1. Anatomy of control systems. Let's look at how this all actually works.
So to really understand the open loop, we first got to understand basic control mechanics. Pretty much any control system out there, no matter how ridiculously simple or complex, operates on this fundamental flow. It always starts right at step 1, the reference input. Now the system takes this input, but it doesn't just blindly throw it at the problem. Internally, the control system is split into two distinct sections. First up, we have step 2, the controller section. Think of the controller as the gatekeeper. It actually regulates the specific amount of input required to make the system function. Once that input is controlled and dialed in, it moves right along to step 3, the process section. This is where the heavy lifting happens. The regulated input is processed here to finally generate step 4, the output. So input to controller, controller to process, process to output. That flow right there, that's your fundamental backbone of control systems.
Moving right along to section 2, defining the open loop. What exactly is it?
So here is the absolute crucial point. An open-loop control system is one where the control action is totally 100% independent of the output of the system. The input that kicks off the whole process, it's entirely disconnected from whatever is actually generated at the end. Once the process begins, they are completely separated from one another. In other words, the input is flying completely blind to the output. Which, naturally brings up a pretty massive question. If the control action is entirely independent of the output, how on earth does the system know when to stop? Like, how does it know if it's actually successfully done its job? If you're heating something up or moving a part and the system isn't ever checking the final results, how does it actually manage to finish the task right?
Well, the stark reality is, it doesn't. Literally, there is absolutely no feedback signal in an open-loop system. There's no clever internal mechanism raising a flag saying, hey, we need to increase the input signal, or, whoa, slow down, decrease the input to get the right output. Nope. It just turns on, runs its process based purely on that initial input, and honestly, just hopes for the best. It's a total one-way street with zero communication coming back the other way. And that brilliantly illustrates the ultimate catch of the open loop. Because the machine itself completely lacks any internal feedback mechanism, human intervention is literally the only thing keeping the system accurate. You, the user, are essentially the feedback loop. Your experience, your timing, your watchful eye, that's what guarantees the output is correct. If you just walk away, the system is going to blindly keep going based on its initial setting, totally oblivious to whether it's succeeding or, causing a complete disaster. All right, section 3, real-life appliance examples. Let's look at some applications. Let's take all this theory and apply it to everyday objects you probably used this very morning. Take the immersion water heater. That metal heating rod you drop directly into a bucket or a cup of water to boil it. When you plug that thing in, it just goes right on heating the water. It has absolutely no feedback mechanism to tell you how hot the water actually is, and it definitely doesn't know when to turn itself off. If you don't step in and physically pull it out, it'll just keep heating until the water completely boils away. And then we have the classic toaster. You push that lever down, and the toaster goes to work increasing the temperature of the bread. But the toaster itself? It doesn't actually know the temperature of your toast, and it certainly doesn't know when to stop heating based on how crispy the bread is getting. It just runs on a blind, simple timer. And honestly, this is exactly why every single one of us has experienced the universal tragedy of perfectly good bread turning into a burnt, smoking mess. The toaster is completely blind to the output. Which brings us to section 4, the open loop advantages. Why even use it? Now you might be thinking about that burnt toast and asking, why on earth would engineers intentionally build something so blind? Well, open-loop systems are actually highly desirable for a few key reasons. First up, they feature a super simple construction and design. Because you don't have to pack them with complex feedback sensors or monitoring software, they are incredibly straightforward to build. Second, because they have fewer elements and very simple circuitry, they're highly economic.
They are cheap to manufacture, and that keeps the cost way down for us, the consumers. And finally, they're incredibly convenient when the output is just too difficult, or maybe too expensive to measure accurately. I mean, think about it. Adding a high-tech, sophisticated temperature sensor to a $10 toaster just doesn't make economic sense when a simple mechanical timer is going to do the job right 90% of the time.
And finally, Section 5, the fatal flaw. Let's talk about the ultimate trade-off.
So the major glaring disadvantage of using any open-loop system is right here. It is incredibly poorly equipped to handle disturbances. Think about it for a second. If the voltage in your house drops, or if the ambient temperature in the kitchen changes, or, here's a big one, if you pop a frozen piece of bread into that toaster instead of a room temperature one, the system simply cannot adjust. It can't alter its input to compensate for those environmental changes because it literally has no idea they're even happening. And because it cannot handle disturbances, it is fundamentally not reliable. You simply cannot trust it to give you the exact same perfect result every single time without human supervision.
Which leaves us with this final, truly vital question. How do we solve this unreliability? How do we actually fix the open loop so we don't have to spend our lives constantly monitoring our machines? Well, according to the principles of control systems, the answer is actually incredibly elegant. To remove these massive disadvantages, we have to add a feedback factor from the output side, routing right back to the input side. By basically giving the system eyes to see its own output, we transform it into what's called a closed-loop system. But how exactly does that feedback factor work? And what kind of crazy new complexities does that introduce? Well, that is a whole other fascinating rabbit hole that we'll have to save for our next explainer. Until then, seriously, keep a close eye on your toast.